Looking over page 2 in your book, basically chapter 1 actually, and this page talks about everything we're going to cover. Everything we're going to cover is right here. We're going to go back over limits, which we ended last year with. We're going to talk about derivatives, integrals, one kind of them, which are the definite integrals, and then integrals another kind, which are the indefinite integrals. So we're going to actually study everything that we're going to cover this year. We're going to explore it in chapter 1. Okay, and so you're going to see all of these concepts revealed to you in 4 different ways. Sometimes we'll look at them graphically. So looking at, for example, the limit, well, if I'm looking at this function here, for example, I'm asking myself, as x approaches c from both the left and the right, what's happening at y? Are they approaching the same y value? Derivative, okay? Derivative, you're going to find out, is basically another word for slope, but it's a special kind of slope, okay? And then integral. Integral is basically the area under a curve. Okay, so what are we doing here? We're doing limits. We're really looking at slope, a special kind of slope, and area. Not too hard. Okay, so that's graphically. Numerically, they'll ask us to compute these and estimate them. As well as algebraically, we'll have to do lots of things where we're using our functions and we're using variables. And then, of course, you're going to be asked to write and to explain. So that's the verbally. Assignment 2 is Chapter 1, Section 1, the concept of instantaneous rate. Your essential question: how do you estimate the instantaneous rate of change? And a lot of times for change, I'm going to use the triangle. It's a mathematical symbol that means change. At a given point in time. Okay, so let's start with a basic Algebra 1 review. We are going to talk about the average rate of change. Oh, except for I can't spell average. So basically, if you think about any maybe graph whose x-axis had time and whose y-axis had distance. So just a very simple example here, but let's say over time I maintain a steady rate. Okay, so maybe an hour goes by and I've gone, what would be a good example here? Let's call it 5 miles. 2 hours go by and now I've gone 10 miles. and so on. 3 hours go by, I've gone 15 miles. Well, basically, my average rate of change here, going from any point on this line to another point on this line, is going to be my slope. It's going to be how far have I gone in so much time. Okay, so that's your change in y over change in x. Just like you've been doing for many years at this point. So we can say that average rate of change is always going to be your slope, where you have change in y over change in x. And you usually find that by subtracting the two y values, right, from this height down to this height, and then the same thing with the x values. So in this example, if I was looking from, what's my average rate of change from 1 to 2 hours, well, basically I'm going 5 miles per hour, right? So that's my average rate of change here, is 5 miles per hour. Okay, so that's just an example. Now, that's all great, but what about at an instant? So, an instant isn't an hour. It's much less than an hour. So we want to talk about now the instantaneous. So this is where things are happening at an instant. Okay, so an instant is basically at time being 0, right? So there's no change happening in time. So basically like 0 seconds or 0 hours. It's happening in an instant, okay? So if it's happening right at that instant where there is no change in time, so here, no change in time, well, let's think about our slope. So this means then, therefore, right, 3 dots, therefore, that my slope, if I tried to calculate it by change in y over change in x, well, at an instant, there is no change in x, right? I'm looking just at that moment in time. Okay, so I might have something on top, but I'm basically 0 on the bottom. There's a problem here. You can't have a 0 on the bottom, right? This is undefined. Which is where calculus comes in. So we're going to learn to deal with this concept. We're going to use the derivative to find the instantaneous rate of change. So this will come, I promise. It just won't come immediately. Okay? So we'll maybe draw an arrow to be clear. Okay, so at this point, we can figure it out, we can estimate it, okay? So we want to get as close to an instant as possible by estimating the rate numerically, okay? So we will get as close to an instant as possible by estimating the rate numerically And in order to do this, we're going to have to find the limit of the average rates as the time interval gets closer and closer to 0. Okay, so we're going to do that by finding the limit of the average rates. So those slopes as the time interval gets closer and closer to 0. We're going to use an exploration to do this. So I have given you guys this exploration 1-1. And you'll notice, now that I'm here talking about this, you'll notice in our book, every time that there's a section 1 in a chapter, it's always going to be some kind of exploration leading you into that chapter and the topic that's going to be discussed in that chapter. Okay. So looking at this exploration, we're going to explore the instantaneous rate of change of a function. So we have a door, and the diagram shows a door with an automatic closer. So at time t equals 0, someone pushes the door. Okay, that's at time equals 0. That's important. It swings open. And then it slows down. Okay, so it's swinging open, it slows down, then it stops. So it goes open, slowing down, stops, start closing again, and then it slams shut at time t equals 7 seconds. As the door is in motion, the number of degrees, d, it is, from its closed position depends on t, time. So we're going to sketch a reasonable graph of d versus t. So go ahead and try and do that. Maybe pause the video so that you can get your mind thinking and not just listening to me. And then come back. All right, so I'm going to first sketch my graph with my two axes. We have t, which is going to be in seconds. And then my vertical axes will be this, let's see, I'll put D. Actually, I'm going to put that vertically. But I'll label it horizontally here. Degrees. Okay. So at time t, well, that's when time is 0. So at time t equals 0, here we are. And the door is not open, right? Okay, but all of a sudden somebody pushes it open. All right, so at first it's going to swing open. It's going to go quite quickly. Okay, but then it starts to slow down, so it's not going to be the same rate of change anymore, right? It's not going to be as steep of a slope. Instead, it's going to have a slightly less of a slope. Then it totally stops. Well, what does that look like? Well, the degrees aren't changing at all, so it's going to have to be something a little bit flatter, or completely flat, I should say, horizontal. Okay, then then the door basically starts to close. Okay, and it's going to probably start off slow, but then as it gets closer and closer to being shut, it's going to end up slamming shut. So I know it's going to end up getting quicker and quicker as it gets to be less and less degrees open. Okay, so it's, let's see, it is time 0 is here, and it needs to shut by time equals 7 seconds. So again, I know it's going to open quickly, then it's going to start to flatten out, then it is going to flatten out, right? This is where it's completely open and changes direction. Then it's going to start closing more slowly and then more quickly. I'll pretend like that's 7. Pretty interesting, right? Hopefully you got that graph. Okay, so now we know an equation to figure out the degrees that it is at any certain time. Okay, so suppose that D is given by the equation right here. Okay, we're going to plot this graph on your grapher. Now your book uses grapher. What a silly word. They mean graphing calculator. So we're going to use our grapher. We're going to sketch the results here. So go ahead and do that in your graphing calculator. I put it into my y equals and then I can graph it. Before you do that though, you want to check your window. And I'm staying in the first quadrant, and I'm going between time equals 0 and 7, so I'm going to go a little bit further. I'll go to 8. And then I'm not really sure what this door looks like and how far open it actually goes, but I imagine it's going to hit a wall. I don't think it would do a 360, so the degrees would be probably at the max 180. Okay, so I'm going to check it out. Let's see. Oh, that looks pretty good. So I'm going to go ahead and sketch that. So this would be at time 7, this would be at time 0. Let's see this here. Well, it's not going to be perfect, but it's an estimate. Okay, and we'll get into a table here. So we're going to make a table of values for D for each second from time equals 0 to time equals 10. Okay, so what's a great way I can do that using my calculator? And I don't mean plugging it into the formula each time. Hopefully you remember a really great feature that we have here is to use our table. So the first thing I want to do is I want to set my table so that it will go from 0 to 10. So table start is starting at 0, so that works for me. And then I can go ahead and I can view my table. So I'm going to go ahead and write down these values. Now, some of these are going to have decimals, and they're asking us to round to the nearest tenth. So let's just see. So I guess these ones don't have decimals. And then once we get down here, we'll just round to the nearest tenth. So that's not too challenging. Moving on to number 4. At time t equals 1 second, does the door appear to be opening or closing, and how can you tell? So let's see. Here's time equals, oops, you can't see that. There you go. There's time equals 1. Okay, so I know that before time equals 1 it was 0. After it was still 100. So I'm not 100% sure what's happening here. I need to investigate a little bit further. And I'm going to do that by breaking down, basically looking around time equals 1 in my table. So maybe I'll look at this a little bit before it and a little bit after it to see exactly what's happening. In order to do that, I'm going to need to use my table again. So I'm going to go back to my table. This time I'm going to set my table. So that I'll start at 1, and I'm going to increase by 100th. Let's see what that table information gives me. So I can see a little bit before, I can see a little bit after. I'm going to go ahead and write that table down. So this would be my T and my D. So at time 0.99 seconds, I'm at 99.7 degrees. And then at 1, we already know that's 100. But at 1.01, I'm at 100.3. So I can definitely conclude here that it's still opening after 1 second, right? So before it was a little bit less, after it's a little bit bigger. So it's definitely opening. we can say something like before 1 second, the door is less than 100 degrees, and after 1 second, it is greater than 100 degrees. Number 5, what is the average rate at which the door is moving for the time interval from 1 to 1.1 seconds? Based on your answer, does the door seem to be opening or closing at time t equals 1? So I think here we're going to go ahead and we're going to make a table of values so that I can get the outputs of both of these. So again, another table to help me organize my information. So at 1, I already know that it's 100 degrees. 1.1, that was not something that I set my table to look at, so I'm going to do that now. So I'll set my table to start at 1, and instead now I'm going to go up by a tenth. So at 1.1 seconds, it's 102.6 degrees. All right, so we need the average rate. How do you find the average rate? That's right, it's basically the slope, okay? So I'm going to find the slope between these 2 points. So again, to find the slope, you basically want your change in y over change in x, okay? And this is going to give us the average rate. All right, so my change in y, well, that's going to be, y2 minus y1. So basically 102.6 minus 100, and then x2 minus x1, so 1.1 minus 1. Okay, do those calculations. You're going to end up with 2.63 over 0.1. Now, it might be really important, actually in calculus it is pretty important, to really think about your units. So what units are we talking about here? Well, the y was going to be degrees, and the x was going to be seconds. So when I get my final answer here, I get about 26 degrees per second. All right, so let's actually answer number 5 now. So based on your answer, does the door seem to be opening or closing at time t equals 1, and you need to explain. So what do you think? Well, it's opening at 26 degrees per second. So is it opening or closing? It's got to be opening. And we know that because we have a positive rate of change. So we've got a pretty, this is our whole answer here. All right, for 6, I think I'm going to go back to our note paper because I'm actually going to draw out a table. So I'm going to use the back side of my note paper. Draw myself a left-hand margin here. So I'm going to make myself a table that's going to involve the things that they're asking for. I'm going to find some average rates. I'm going to have some different time intervals that I'm going to be working with here. So I'm going to want a little bit more room. I don't think that they gave us enough room here. So starting out with, the time and the degrees. But then I want to find that average rate of change, which is basically change in y or change in d over change in t. And then all together, I'm going to have another column that's going to say, hey, well, what is the average rate? Okay, so we're going to use the time intervals 1 to 1.01, then 1 to 1.001, and so on, okay, to make a conjecture about the instantaneous rate at which the door is moving at time t equals 1. So let's check this out. So we're going to go 1, we'll also do 1.01, and then 1.001, and then 1 point, how about 0.0001? How about 1.12341? All right, so we're going to use our table to help us get some of these values. We already know what's happening at 1. That is 100. We already had 1.01. That was 100.3. And I'm going to go back and I'm going to get some more decimal places to help have exact answers. Just going to 0.1 is not going to give me exact enough answers. So I am going to go back to my table. I think before I do that though, no, that's exactly what I'm going to do. So let me set my table. Start at 1. I'm going to go up by 100th. See, and it's got all of these decimals that follow after it. So I think I'm going to go to the 4 there. Let's see what I can fit on here. 30234. Okay. I'm going to do the same thing for 0.001. So I'm getting 100.03064. And let's just go up. Can I insert a 0? There we go. So that's going to be 100.003. I've got 068. And I need one more 0 here. One, two, three, 4 zeros is what I'm looking for. So that's going to give me 100 point, 1, 2, 3. Basically the same thing. Okay, so I think we're getting really, really close here. All right, so from there, now I've just got a whole bunch of math I need to do. So basically, I'm going to find the slope between these two. Okay, I'm going to find the slope between these two, find the slope between these two, and so on. So just to give you an example, and then I'm not going to do all this work, but we'll take 100.30234 minus 100, which is my original. Now I'm going to look on the x-axis, or the t, that's seconds, and I'm going to do 1.01 minus 1, and so that's going to give me about 30.234 degrees per second. Okay, and then you're just going to keep doing the same work. So I'll do the next one one more time, write it out. So I'll take this number, subtract that number. These are like my y's, or basically my vertical axes. So 100.03064 minus 100. Okay, and I'm just trying to show you guys where all these numbers come from. And when you plug that into your calculator, you're going to end up with 30.64 degrees per second. Okay, so the next two, you'd find the exact same slope, because they have the exact same numbers, right? So that might be considered a limit. So when you actually take this and subtract that, you're just going to be left with this, right? Divided by, if you take this and subtract that, you're just going to be left with this. And when you divide those, you're going to end up with 30.68 degrees per second. And this becomes the exact same thing. 30.68 degrees per second. Okay, so back to the question. Make a conjecture about the instantaneous rate at which the door is moving at time t equals 1 second. Well, as the time between, as we get closer and closer and closer to time change being 0, right? And we can keep doing this. You could do this all day long. But see how this time change is going from, well, this was 1.0 to now 1.000. Right? There's like no time change barely. We're getting down to that like instant or instantaneous rate. And we're noticing that we are approaching basically like 30.68 degrees per second. That's kind of our limit of these average rates. Okay, as time approaches, as the change in time approaches 0. So really, and originally the problem wanted us to round to the nearest tenth. So I can say, well, my instantaneous rate is probably going to be 30.7 degrees per second.